Hi students, in this interesting chapter, we're going to study about the grouping of batteries and measuring instruments. You see, there are various instruments to measure current, to measure voltage like the ammeter, the voltmeter and so on. There's even a device called potentiometer. All of these instruments are important for the IIT JEE syllabus. So we'll study about how they work and we'll solve some problems related to these instruments. Also, did you know that batteries can also be grouped in series and parallel combinations, just like resistors and capacitors? We'll do that in this chapter. We'll connect batteries in series and we'll try to calculate the equivalent electromotive force of the battery. So let's begin with this interesting chapter related to batteries and measuring instruments. Here we go. Now before we study about the grouping of batteries or measuring instruments, we learn about a small concept that we haven't yet talked about, the concept of the internal resistance of a battery. You see, every battery actually has a resistance attached to it. How does a battery function? A battery functions when the chemicals inside the battery react. Some electrolyte causes the ions to flow from one end of the battery to the other end of the battery. So there is some resistance in the solution of the battery, which stops the ions from flowing freely. So all batteries have some amount of internal resistance to the flow of current. What this means is that instead of replacing a battery by this symbol always, we should actually practically replace a battery with this symbol. So a battery consists of an EMF, electromotive force E, and an internal resistance small r. And the net potential difference between the terminals of the battery is VA minus VB, the potential difference between the points A and B, not just E. And as I just said, this resistance is because of the resistance inside the solution of the battery to the flow of ions inside the battery. The term E here is electromotive force. It is the ideal potential difference that should have been created in the battery had there been no resistance offered to the flow of ions. And up till now in our study in electric current, we had neglected internal resistance. Like we had assumed that there's only this battery with zero internal resistance. But now, since we are moving towards more practical situations, we'll also consider the internal resistance of a battery. Now that we know that the internal resistance of a battery exists, what will be the potential difference between the terminals of a battery? Well, let's say this battery is actually emitting a current I. That is, the current I is flowing out of the positive terminal of the battery and it is entering the negative terminal of the battery. In such a case, if we apply modified Kirchhoff's law, we'll see that VA, the potential of the point A, minus E plus I into R equal to VB, isn't it? You see, when we are moving from left to right, we will write minus E because the potential of the battery is positive to the left and negative to the right. Similarly, we'll write plus IR because when we're moving from left to right, we're moving against the direction of the current. So the potential is increasing, the potential difference across the internal resistance. So that is the reason we'll say VA minus E plus IR is VB. Now if we fiddle with this equation a bit, we actually get VA minus VB equal to E minus IR. What this means is that the net potential difference across the terminals of a real battery is not E, the electromotive force of the battery. It's actually equal to E minus IR, where I is the current flowing from the battery and R is the internal resistance of the battery. So in normal conditions, when the battery is actually charging the rest of the circuit, it's providing current to the rest of the circuit. In such conditions, the net potential difference of a battery is actually less than the ideal potential difference expected across its ends. Understood? So this is something you must remember. The potential difference across a battery is E minus IR when the current is coming out of the battery. Now we can have a weird scenario, when the battery has been short circuited. Now if there were no internal resistance and you simply connected the negative end of the battery to the positive end of the battery, something like this. In that case, the battery would get damaged because you see the electrolyte inside the battery is actually working to create a positive terminal here and a negative terminal here. But when we connect the positive and the negative terminal, we nullify the effects of that electrolyte and the battery gets damaged. In fact, a very strong reverse current will flow through the battery, and that will actually neutralize the battery, that will destroy the battery, because it will not let a new potential difference be created in the battery. But something different and quite ordinary happens in the case when we have an internal resistance. In this case, a finite current starts flowing in the battery when there's a battery with an internal resistance and you short circuit the two terminals of the battery. Why does this happen? Because the internal resistance actually behaves, just as an external resistance would behave if it were connected with a battery. You see, VA is equal to VB, and VA minus VB is 0. So I is E by R, because as you can clearly see, plus E minus IR is 0, isn't it? So a current equal to E divided by R flows inside this short-circuited circuit. Understood? It's weird, but this is what happens when a real battery with a real internal resistance is short-circuited. A current flows through a battery even though no other circuit element is connected to the battery. Another interesting case related to real batteries with real internal resistances is when a battery is being charged. In many cases, over time, the potential difference across the battery slowly decreases and the battery needs recharging. The battery is generally recharged using another battery. And when another battery is recharging this battery, current is actually flowing into the battery, isn't it? After all, the battery is being recharged. So as you can see, this is how the current is flowing. The current is entering the positive terminal of the battery and leaving the negative terminal of the battery. In such a case, what will be the potential difference across the two ends of the battery, A and B? Well, we can apply modified Kirchhoff's law to find out. You see, in such a case, VA, the potential at the point A, minus E minus IR equal to VB, isn't it? That's simple enough. I've written minus E because the potential of the battery is decreasing from left to right. I've written minus IR because left to right is the direction of the flowing current, and in the direction of the current, the potential difference across a resistor decreases. Therefore, when we simplify this expression, we get VA minus VB equal to E plus IR. This is again interesting. What this tells us is that when a battery is being charged by another battery, in that case, the net potential difference across the battery is more than the electromotive force of the battery. Remember, this is quite different from the case when the battery was charging the other circuit elements, and when the current was flowing out of the battery. In that case, VA minus VB was E minus IR. So, the potential difference across the battery terminals does depend quite a lot on the internal resistance of the battery. In fact, we can consider all the three cases that we just looked at. When the battery is supplying current to the circuit, the potential difference across the battery is E minus IR, where R is the internal resistance of the battery and I is the current flowing out from the positive terminal of the battery. In short circuit condition, the electric potential across the battery terminals is 0, and that has to be so. After all, we've connected, the positive terminal of the battery to the negative terminal of the battery. But a current I equal to E by R does flow through the circuit even when the battery is short circuited. When the battery is getting charged by another battery, in that case, the net potential difference across the terminals of a battery is E plus IR, that is more than the electromotive force of the battery. R here is the internal resistance of the battery. So of course, you have to remember all these three conditions. As we'll use internal resistance in solving problems, you'll slowly get the hang of what exactly the internal resistance is. For now, let's move on to the next concept. Our next concept is series grouping of cells. Consider this circuit that you see on your screen. You can see three batteries, each of EMF E. You can see that each battery here has an internal resistance small r. And you can also see there's an external resistance capital R connected in the circuit. Now, if you had to replace all the 3 batteries here with one single battery, and if you had to replace all the internal resistances here with one single internal resistance, then what would be the value of that one single battery and that one single internal resistance? That is what we intend to calculate here. As you can see, these batteries and internal resistances are arranged in series. They're arranged one after the other. The first thing we can do is calculate the current in the circuit. You see, if the current in the circuit is I, in that case I is clearly E equivalent divided by R plus R equivalent, isn't it? Because if we replaced all these batteries with one single battery of EMF E equivalent and one single internal resistance R equivalent, in that case the current in the circuit I would be E equivalent divided by capital R plus small r equivalent, isn't it? So what we can do is, we can actually calculate the current in this circuit, and then we can equate the numerator to E equivalent, and in the denominator we can equate this term apart from the capital R to R equivalent. In that way we can find out the values of the equivalent EMF and the equivalent internal resistance in case of series grouping of cells. So here we go. The current in the circuit is clearly 3E divided by R plus 3R, isn't it? Because as you can see, if you apply Kirchhoff's law, you'll see that plus E plus E plus E minus I into capital R minus 3R into I is 0, isn't it? Now what this means is that the equivalent EMF is actually 3E, isn't it? And it also means that the equivalent internal resistance is R equivalent. Interesting, isn't it? Now, since E equivalent is 3E when 3 cells are connected in series, E equivalent is actually NE when N cells are connected in series. So basically, in series grouping of cells, the net equivalent EMF is the sum of all the individual EMFs of all the cells. Similarly, the net internal resistance is the sum of all the individual internal resistances of each of the batteries. So this is the formula for series grouping of cells, and you of course must remember it. Now what happens in case of parallel connections? Well, let's see. Let's assume that E1 and E2 are the EMFs of 2 cells connected in parallel with the resistance capital R. Small r1 and small r2 are the internal resistance of these 2 batteries E1 and E2. Now again, in this case, how will we calculate the equivalent cell of EMF E equivalent and internal resistance small r equivalent that can replace both these cells? Simple. We'll again apply Kirchhoff's law and try to calculate the current in the circuit. If the current through the capital resistance R is actually I, in that case I will be equal to E equivalent divided by R plus R equivalent. So we can calculate an expression for I, the current through the capital resistance R, and then using this expression we can compare this expression to the expression we obtain, and thus obtain the value of equivalent EMF and equivalent internal resistance. So there, let's apply Kirchhoff's laws. When we apply Kirchhoff's law in the loop having the battery E1, the internal resistance R1 and the resistance capital R, in that case, when we apply Kirchhoff's law in the anti-clockwise direction, we get plus E1 minus I into R minus I minus I1 into R equal to 0. That is because if a current I1 is flowing from here and a current I minus I1 is flowing from here, then a current I must be flowing here, isn't it? Because using Kirchhoff's current law, we can say that the sum of the currents in these 2 branches, this one and this one, is the same as the net current in this branch. So that is the reason we can apply this particular equation for the loop consisting of battery E1 and resistance R, like this, in this direction. Plus E1 minus I into R minus I minus I1 into R equal to 0. Similarly, we can apply Kirchhoff's voltage law in the loop consisting of the battery E2, internal resistance R2 and the resistance capital R. When we do so, we get plus E2 minus I into capital R minus I1 into R2 equal to 0, isn't it? As you can see, I is the current flowing through the resistance capital R and I1 is the current flowing through the internal resistance of the battery E2, isn't it? So when we simplify both these expressions and basically we eliminate the variable I1 from both these expressions, then we get the net value of the current through this circuit as this expression. Now this current I is basically the current flowing through the resistance capital R. Now remember, I had just said that if we replace both the batteries with a battery of EMF E equivalent and internal resistance R equivalent, in that case I had said that I is equal to E equivalent divided by R plus R equivalent, isn't it? Now in this case, if you equate both these expressions, this one and this one, what you will see is that this numerator here is actually E equivalent, isn't it? And you will also see that this capital R is this capital R here, and this expression here represents R equivalent, the equivalent internal resistance of a connection of batteries in parallel. Therefore, when we equate both these expressions, we get the value of E equivalent as this expression, and we get the value of R equivalent, the internal resistance of both the batteries combined, as this expression. In general, we can say that E equivalent for any number of batteries in parallel is sigma E by R divided by sigma 1 by R. What this means is, let's say you have two batteries in parallel, E1 and E2, which have resistances R1 and R2. In that case, E equivalent will be equal to E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. If again you have three batteries, E1, E2 and E3 with internal resistances R1, R2 and R3, in that case E equivalent will be equal to E1 by R1 plus E2 by R2 plus E3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3, isn't it? So basically this will be the expression for the equivalent EMF in the case when batteries are connected in parallel with each other. What will be the expression for the internal resistance when any number of batteries are connected in parallel with each other? The internal resistance R equivalent will be such that 1 by R equivalent will be 1 by R1 plus 1 by R2 plus 1 by R3 and so on. That is, 1 by R equivalent will be sigma 1 by R. Of course, you must remember both these expressions, this one and this one here. So basically, the circuit that we saw on our previous screen can actually be replaced by this circuit. It can be replaced with a battery of EMF E equivalent, an internal resistance R equivalent, and of course our resistance capital R. So that was our study of batteries and internal resistances and batteries in series and parallel connections. Let's now move on to a topic that is very important for IIT JEE, measuring instruments. The first measuring instrument that we must study for IIT JEE is the galvanometer. Since the last few years, many problems related to measuring instruments have come up in IIT JEE. In fact, almost every year these days, there's one problem related to a measuring instrument. So yes, you must put special emphasis on this topic. First of all, let's try to understand what a galvanometer is. Now, a galvanometer is an instrument that actually shows deflection when a current is passed through it. So you see, if you have this galvanometer that you see on your screen, the needle of the galvanometer is at rest initially. But when we pass current through this galvanometer, it shows deflection like this. So this is a very important instrument because in many electrical circuits, we have to detect the presence of current. Is the current flowing or not flowing? So all you have to do is connect a galvanometer in the circuit. Now, what are the basics of how a galvanometer works? We do not need to study those basics in detail, but what really happens is, that inside this galvanometer, there's actually a permanent magnet. Something like this. a permanent magnet, and there's also a coil of wire like this. The electric current that we pass through the galvanometer actually passes through this coil. Now, we'll study later in the chapter related to magnetism that when a current carrying coil is placed in a magnetic field, it experiences a torque. So this coil basically experiences a torque because it is placed in the magnetic field of this permanent magnet. The galvanometer construction is such that this coil experiences a reverse torque because of some springs that are attached to this coil like this. And this reverse torque is actually proportional to the current passing through the galvanometer. Now this might seem weird and even sort of hazy, but then we haven't studied magnetism yet, and when we study magnetism, the reason related to why the coil rotates will become clear. But the fundamental thing that you must understand is that the galvanometer has a coil placed in a magnetic field, and this coil experiences a torque. The torque experienced causes the needle to move here, and the movement of the needle, the rotation of the needle, is proportional to the magnitude of the electric current. So for example, if you pass a 2 ampere current and then you pass a 4 ampere current, then you see the deflection in the needle will be twice for the 4 ampere current compared to when the 2 ampere current was passed. Understood? So that's the basic concept of a galvanometer. Did you, however, know that a galvanometer is actually used in many daily applications? For example, the speedometers of your car, the car instrument panels, they use a galvanometer. Similarly, laser light. You must have seen lasers, at one time or the other. Lasers are even used for eye surgery these days. So galvanometers are even used in constructing laser systems. So galvanometers are not so far apart, from our daily life. They are a part of our daily life too. Now, the galvanometer deflection, as I just told you, is proportional to the electric current. The galvanometer resistance is generally denoted by G. So, if you connect a galvanometer in a circuit, what will be the effect of the galvanometer? Well, the galvanometer will offer a resistance equal to a value G, the resistance of the galvanometer. Now, if the galvanometer offers a resistance G, the net potential difference across the galvanometer will be Ig into G, where Ig is the current passing through the galvanometer. So there you go. This formula is useful when you connect a galvanometer in a circuit and you have to study the effect of the galvanometer on the circuit. So in those cases, you can consider the resistance of the galvanometer to be G and the current passing through the galvanometer to be Ig. The potential difference across the galvanometer is Ig into G. In general though, when we connect a galvanometer, we neglect its resistance and assume that it's not that comparable to the values of the other resistances in the circuit. So that was the basic explanation of the details of the galvanometer. Another very important instrument that's almost similar to a galvanometer is the ammeter. An ammeter is a current measuring instrument. So there's a small difference between a galvanometer and an ammeter. An ammeter actually tells you the value of the current, while a galvanometer just tells you whether the current is there or not there. A galvanometer can be modified to convert it into an ammeter. How can it be modified? Well, all you have to do is you have to connect a resistance called shunt in parallel with the galvanometer. When you do that, the galvanometer becomes an ammeter. The shunt resistance, this resistance here, is very, very small in value. It's of the order of 0.2 ohms, 0.5 ohms, something like that. So when you connect a shunt resistance to a galvanometer, you can use the galvanometer to detect accurate current readings. Now, there could be a simple doubt here. Why is a galvanometer not enough to detect the current reading? You see, we already know that the deflection in a galvanometer is such, the deflection is proportional to the current, isn't it? If that is so, you can graduate the galvanometer scale in such a way that the galvanometer can be used to detect the value of current. What is so special about connecting a shunt resistance with the galvanometer? Like, how does that help us detect current better? You see, there's a small problem when we use only a galvanometer to measure current and when we don't use the shunt resistance. Let's see what that problem is by actually connecting a galvanometer in a circuit. Here we go. Circuit, galvanometer. Now the net current passing through the circuit when the galvanometer is connected in the circuit is V divided by RC plus G, isn't it? After all, if V is the net potential difference in the circuit, the potential difference across the battery source, and if RC is the resistance of the circuit and G is the resistance of the galvanometer, then clearly the net current will be V divided by total resistance. That is V divided by RC plus G, resistance in the circuit, plus G, isn't it? There's no doubt about it. Now the problem here is that this is the current that the galvanometer will detect, isn't it? And so the reading of the galvanometer will be proportional to this current reading. Now the actual current in the circuit when the galvanometer was not connected at all was V divided by RC, the potential difference across the circuit, divided by the resistance present in the circuit. So the current has actually changed because of the presence of the galvanometer, and so the galvanometer reading will be wrong. The galvanometer reading will tell us the new current when the galvanometer is itself connected in the circuit, but the actual current is V divided by RC when there is no galvanometer. Now how do we obtain an accurate reading? To obtain an accurate reading, we need the value of G to be very small, isn't it? After all, if the galvanometer resistance is very, very small, then in that case, the net current in the circuit will be V divided by RC plus a very small value, isn't it? And this very small value can almost be taken to be 0. So the net current in the circuit will then be approximately the same as the actual current, V divided by RC. Now to make sure that the galvanometer resistance is very small, we connect this shunt resistance in parallel with the galvanometer. You see, it has been found out that if there are two resistances R1 and R2, in that case, the equivalent resistance in case of a parallel connection between R1 and R2 is always less than R1 and it is less than R2. So that means if G and S are connected in parallel, in that case the net galvanometer resistance is less than G and it is less than S. You can even verify this. Let's take a 3 ohm resistor and a 4 ohm resistor in parallel. In that case, the equivalent resistance of 3 ohm and 4 ohm will be 3 into 4 divided by 3 plus 4. That is 12 divided by 7, which is approximately 2.7 ohms. So as you can see, 2.7 ohms is less than 3 and it is less than 4. In general, the equivalent of a parallel combination is less than each of the two resistances. What that means is that the net resistance of the galvanometer shunt system is actually less than the resistance of the shunt. And since the resistance of the shunt is very small, of the order of 0.2 ohms or 0.1 ohm, the net resistance of the galvanometer shunt system, the net resistance of the ammeter is very, very small. Therefore, the new ammeter, the modified galvanometer, it detects a current approximately equal to V by RC, where RC is the resistance of the circuit. It does not detect a current equal to V by RC plus G, because G has a very small value in this case. Understood? So that is the reason why we actually connect the shunt resistance in parallel with the galvanometer to convert it into an ammeter. So that was the principle of the ammeter. As I just told you, the shunt has a very small resistance, so it decreases the net resistance of the ammeter. You can actually apply Ohm's law in this circuit and say that Ig into G is the same as I minus Ig into S. So in some problem, if you have to calculate the shunt resistance, this is what you can use. S is Ig by I minus Ig into G, because the potential difference across these two terminals is the same. Ig into G equal to I minus Ig into S. One important fact related to the ammeter is that the ammeter is always connected in series with the circuit. Now this is obvious. After all, we already know that in case of series connections, the current is the same, isn't it? And since the ammeter measures current, it has to be connected in series with the circuit. If this is the circuit here, then the ammeter can be here. If the ammeter was actually connected in parallel with the circuit element, like this, it would not detect the current inside the circuit, isn't it? Because it's in series that the current is the same. So the ammeter is connected in series always. The next instrument we're going to study, and which is very similar to the ammeter and the galvanometer, is the voltmeter. A voltmeter measures the potential difference between 2 points. A voltmeter is also basically a modified galvanometer. So just as the ammeter involved connecting a resistance in parallel with the galvanometer, a voltmeter involves connecting a resistance R in series with the galvanometer. So as you can see, the system you see on your screen here represents a voltmeter because it has a very large resistance R connected in series with the galvanometer. As I just said, the value of R is generally taken to be very large, hundreds or sometimes even thousands of ohms. So why do we have to connect a resistance R with the galvanometer to measure the potential difference? Why can't we simply use a galvanometer? After all, the galvanometer deflection is proportional to the electric current, and we know that by Ohm's law, the potential difference across 2 points is also proportional to the electric current. So somehow we could have, graduated the galvanometer to measure the electric potential. So why do we connect this resistance R? Well, if we connected only a galvanometer and used it to measure the potential difference across a circuit element like this, in that case there would be one small problem. You see, the net potential difference detected by the galvanometer would be Ig into G, isn't it? Where Ig is the current passing through the galvanometer. So you see, if the net current coming into the circuit element is I, then Ig current would pass through the galvanometer, and I minus Ig current would pass through the circuit element, isn't it? Now the problem with this is that the net potential difference detected by the galvanometer would be Ig into G, which would be the same as I minus Ig into RC, say if the resistance of the circuit element is RC. So the potential difference detected is I minus Ig into RC. But what is the actual potential difference across the circuit element? If the galvanometer just wasn't there, the actual potential difference would be I into RC, where RC is the resistance of the circuit, isn't it? The potential difference across the circuit element would have been I into RC had there been no galvanometer. Now with the galvanometer present, the potential difference is I minus Ig into RC because some of the current is taken up by the galvanometer. Now the important point here is that if Ig is very small, in that case I minus Ig into RC would approximately be equal to I into RC. That would mean that almost all of the current is passing through the circuit element and a very small value of current is passing through the galvanometer. Now this can be so if a very large resistance is connected across the galvanometer in series, because in that case a very small current will pass through the galvanometer as a very large resistance has been connected in series with it, and so I minus Ig will approximately be equal to I, the initial original current passing through the circuit element. And that is the reason we connect this resistance, a very large resistance, in series with a galvanometer. Understood? There you go. Now as I said earlier, this resistance connected in series with the galvanometer must have a very large value. You can simply apply Ohm's law and say that the net potential difference measured by the voltmeter is Ig into G plus R, isn't it? Because Ig is the current passing through the galvanometer and the net resistance across the galvanometer and resistance system is G plus R. A voltmeter is always connected in parallel with the circuit element, unlike an ammeter, which was connected in series with the circuit element. That is because, as we already know, the potential difference is the same in parallel. It is not the same across each element in series connections, isn't it? So for example, if there is this resistance, the RC here, in that case if I connect a voltmeter here, then the potential difference will not be the potential difference across the resistance. However, if I connect a voltmeter here in parallel with the resistance, the potential difference across the voltmeter will be the same as the potential difference across the resistance. So that is the reason a voltmeter is always connected in parallel with the circuit element. So there, you've understood the basics of a galvanometer, you've understood the basics of ammeter, the current measuring instrument, and a voltmeter, the voltage measuring instrument. The only difference between a galvanometer, ammeter and voltmeter is that in case of an ammeter, a resistance is connected in parallel with the galvanometer, and this is a very small resistance. In case of a voltmeter, a very large resistance is connected in series with the galvanometer. That is all. Let's now solve a problem to clear our concepts related to ammeter and voltmeter better. What resistances must be added to convert a galvanometer of resistance 100 ohm with a maximum deflection current of 1 milliampere flowing through it into a voltmeter and ammeter? The ammeter range should be from 0 to 50 milliamperes and the voltmeter range should be from 0 to 10 volts. The question definitely seems complicated. Of course, it isn't really complicated once we draw the diagram and see what's happening. So let's draw the diagram. We are basically given a galvanometer which allows a maximum current of 1 milliampere to pass through it. So if there's a current greater than 1 milliampere, the galvanometer will go wrong. The current passing to the galvanometer has to be 1 milliampere or less. Now we want to convert this galvanometer into a voltmeter first. To convert this galvanometer into a voltmeter, we will definitely add a resistance in series like this. So what resistance R must we add to this galvanometer? Now you see, it is given that the voltmeter that we want to make should have a range from 0 to 10 volts. What this means is that the maximum voltage detected by the voltmeter should be 10 volts. So the maximum potential difference from this point to this point must be 10 volts, isn't it? Now we know that the potential difference detected by the galvanometer is actually proportional to the current passing through the galvanometer by Ohm's law. V is IR. So when the maximum voltage is measured by the voltmeter, that's when the maximum deflection current will pass through the galvanometer. So you can basically say that 10 volts here is equal to 1 divided by 1000 amperes into G plus 1 divided by 1000 amperes into R. Isn't it? The net potential difference across the galvanometer resistance system, the voltmeter, is 1 milliampere into G plus R. Isn't it? Now we are given that the resistance of the galvanometer is 100 ohms. So basically the value of G is 100 ohms. In case of maximum voltage, this is the expression. 10 is 1 by 1000 into 100 plus R. That gives us the value of R as 9900 ohms. So basically the net resistance that must be connected in series with the galvanometer to turn it into a voltmeter is 9900 ohms. All we did in this case was that we considered what the maximum voltage measured by the voltmeter was, and we equated it to the maximum possible potential difference across the voltmeter. That's all we did. Now how do we convert this galvanometer into an ammeter? Again simple. All we have to do is add a resistance in parallel with the galvanometer. Now what resistance must we add in parallel with the galvanometer? That is what the question asks us. Now we know that the maximum current that can pass through the galvanometer is 1 milliampere, isn't it? Now when 1 milliampere current passes through the galvanometer, that is when the galvanometer will show its maximum reading and the ammeter will show its maximum reading. We know that the maximum reading for the ammeter is 50 milliamperes because it is given that the range of the ammeter is 0 to 50 milliamperes. What this means is that the ammeter will show a reading of 50 milliamperes when a current of 1 milliamperes passes through the galvanometer, isn't it? Because the maximum ammeter reading will be when the maximum galvanometer reading will be. And because this is so, we can say that 1 milliampere into the resistance of the galvanometer is equal to the shunt resistance into 50 minus 1. You see, when 1 milliampere will be passing here, 50 milliampere will be coming like this, and 49 milliamperes will be passing through the shunt resistance. So basically you can say that 1 into G is 49 into R, isn't it? G is given to be 100. So 1 into 100 is 49 into R. Simplifying this expression, we get the value of R, the shunt resistance, as 2.5 ohms. So basically, a resistance of 9900 ohms must be connected in series with the galvanometer to convert it into a voltmeter. A resistance of 2.5 ohms must be connected in parallel with the galvanometer to convert it into an ammeter. All that we did in this case was basically apply simple logic and apply Ohm's law. That's all we did. You can go through this problem once again to carefully understand the nuances of an ammeter and a galvanometer. To clear our concepts even further, we'll solve yet another problem. This problem was asked in IIT JEE 2005. A moving coil galvanometer of resistance 100 ohms is used as an ammeter using a resistance 0.1 ohms. The maximum deflection current in the galvanometer is 100 microamperes. Find the current in the circuit so that the ammeter shows maximum deflection. Well, after the previous problem, this problem seems to be slightly easier. Again, as in the case of most IIT JEE problem, this problem will become much simpler once we draw a diagram. Here we go. This is what is given in the question. As you can see, it is given that there's this galvanometer and the maximum current that can flow through the galvanometer is 100 microamperes. The resistance of the galvanometer is 100 ohms. The resistance, the shunt resistance connected in parallel with the galvanometer is 0.1 ohms. We have to calculate the net current flowing through the circuit. Now, what will be the net current flowing through the circuit? It will be this current here. As you can see, if the net current is capital I, then capital I is equal to small I plus 100 microamperes, isn't it? So in case of maximum deflection, we have to calculate the net current flowing in the circuit, which is I plus 100 microamperes. Now, we can calculate the value of I by equating the potential difference between these 2 points. You see, by equating the potential difference across the galvanometer and across the shunt resistance, you see the potential difference across the galvanometer is clearly 100 microamperes into 100 ohms, 100 into 100. And the potential difference across the shunt resistance is 0.1 ohms into I microamperes, isn't it? So using this formula, we can calculate the value of I, the current passing through the shunt resistance. Then clearly, the net current passing through the circuit will be I plus 100 microamperes, isn't it? So there you go. I comes out to be 10 raised to 5 microamperes when you simplify this expression. So the net current passing through the circuit is 100 plus 10 raised to 5 microamperes, that is 100.1 milliamperes. This is the value of the net current passing through the circuit, such that the galvanometer has 100 microamperes passing through it and the shunt resistance has 10 raised to 5 microamperes passing through it. Understood? This problem might seem a bit complicated, but all that it really involved was applying Ohm's law. That's all we did, isn't it? All you need to really understand to solve all kinds of voltmeter and ammeter problems is that in case of an ammeter, a shunt resistance is connected in parallel with the galvanometer, and in case of a voltmeter, a resistance is connected in series with the galvanometer. Let's now move on to the next instrument, the instrument called a potentiometer. A potentiometer is an instrument used to calculate the EMF or internal resistance of an unknown battery. You see, you can calculate the EMF of a battery simply by using a voltmeter, isn't it? But a voltmeter has a limitation to it. As we saw in the previous case, the limit of the voltmeter was 10 volts. So voltmeters cannot measure a large value of potential difference. They measure only potential difference up to say 10 volts or maximum 15 volts. If you have to measure the potential difference of a battery which has a voltage EMF of 20 volts, something like that, in that case you need to use a potentiometer. The extra advantage of a potentiometer is that you can also measure the internal resistance of a battery using a potentiometer. First of all, let's take a look at how we can measure the EMF of an unknown battery using a potentiometer. A potentiometer basically consists of a battery of known EMF, E1, and a resistance wire AB. So as you can see, this E1 battery here is connected to the resistance wire AB. A, C and B, as you can see here. Now the unknown battery whose EMF we have to measure is E2. As you can see, one end of this unknown battery is connected to the end B of the potentiometer. The other end is free to move. So basically end C is free to move. E2 is the battery whose EMF we have to determine. Now what do we do to actually determine the EMF of E2? We keep moving this jockey C. You see, this point C is called the jockey. So we keep moving it from left to right and right to left. We keep moving it until the galvanometer shows zero deflection. The point at which the galvanometer shows zero deflection represents the point at which I2 is zero. I2 is the current flowing because of the battery E2 through the resistance AB. I is the current flowing because of the battery E1 through the resistance AB. So basically you can say that the current here is I. The current here is I1 plus I2. Now we keep moving the jockey, from A to B until we obtain zero deflection in the galvanometer. When there is zero deflection in the galvanometer, what that means is I2 is zero. And when I2 is zero, you can say that the only current in CB is I. In fact, the only current in AB is I. Why does I2 become zero? I2 becomes zero because if you apply Kirchhoff's law in the second loop, you will see that E2, in fact plus E2 minus I1 plus I2 into RCB, the resistance between the points C and B, is clearly zero, isn't it? So if you simplify this expression, you get I2 is equal to E2 minus I times RCB divided by RCB. Now this expression has a negative sign here, and at a particular value of CB, the distance between C and B, E2 becomes equal to IRCB. And it is at that instant that I2 becomes 0. And therefore, we can determine the value of E2 by saying that since I2 is 0, E2 is equal to I times RCB. Here you go. Since I2 is 0 at the point C, E2 is I times RCB, isn't it? You can even make that out from this circuit again, because as you can see, the current flowing from C to B is now only I. So plus E2 minus I into RCB is 0, or E2 is I times RCB. So we can determine the value of E2 if we get to know the current in the first loop. But a potentiometer makes it even easier to measure the value of the EMF of cell E2. That is because, you see, in practical laboratories, what we do is we place a known battery instead of E2 here. When we place a known battery, we actually obtain the I2 equal to 0 point at a length L1. When we do that, just as we said that E2 is I into RCB, we say that E known, the EMF of the known battery, is I times RCB. So we say that the EMF of the known battery is I times RCB. And if we consider the resistance per unit length here to be rho, in that case we say that it is equal to I times rho into L1, isn't it? Then we put an unknown battery, you see, just like our E2 unknown battery, and then we again calculate the point at which I2 is 0, the current through the second loop is 0, and for that point we again say that E unknown is I times rho into L2, because L2 is the distance between C and B in this case. And now we basically say that E unknown by E known is L1 by L2. Understood? And that is how we determine the EMF of an unknown battery. Now I know this must have sounded very confusing because it is slightly tough to understand the principle of a potentiometer. So I will repeat what I just said for you. You see, in the case of a potentiometer, we place the unknown battery here below the resistance wire AB. Now we move the jockey in such a way that the current in the second loop becomes 0. Now if the current in the second loop becomes 0, in that case the EMF of the unknown battery is I times RCB, the resistance between C and B. To make things easier, we first put a known battery instead of the unknown battery here. Then we calculate the current equal to 0 point for this known battery. So for the known battery, clearly E known is equal to I times RCB, that is I times rho, if rho is the resistance per unit length, into L1, isn't it? If L1 is the length CB for which I2 is 0. Similarly, we then put an unknown battery. We remove the known battery and we put an unknown battery here. For the unknown battery, E unknown is I into RCB again, that is I into resistance per unit length into the new length CB, that is L2. Now we divide both these expressions to get the formula E unknown by E known equal to L1 divided by L2, where L1 is the length of CB for which current through E known is 0 and L2 is the length CB for which the current through the unknown battery is 0. Understood? Carefully look at what I have said. Replay this portion of the video and I'm sure you'll understand it. All that we basically did was that we first put a known battery and then we put an unknown battery and we took two readings, L1 and L2, for which the current was 0. Then we divided both these readings. In most competitive exam problems, you will be given the value of E known, L1 and L2, and you will simply have to apply this formula to get the value of E unknown. Remember, when talking about a potentiometer, I had also said that a potentiometer can be used to calculate the internal resistance of a battery. How can we calculate the internal resistance of a battery using a potentiometer? Before we learn to calculate the internal resistance of an unknown battery using a potentiometer, let us first try to calculate the internal resistance in a normal circuit consisting of a battery and an external resistance capital R. You see, in an ordinary circuit consisting of a battery of EMF E, an internal resistance small r, and an external resistance capital R, we can apply Kirchhoff's law and we can say that E minus IR minus I into small r is 0, isn't it? That is simple enough. If we consider the net potential difference across the battery to be V, this one here, the one shown on your screen, in that case we can also say that V minus I into capital R is also 0. There is no doubt about it. From these two equations, we can simplify to get the value of small r, the internal resistance in terms of the EMF V, the net potential difference across the battery V, and the external resistance capital R. So we can say that in any circuit consisting of the battery with an internal resistance and an external resistance capital R, small r will be R into E by V minus 1, isn't it? Now that we know this formula, we can use this formula to calculate the internal resistance of an unknown battery using a potentiometer. So let's do it. Here's our potentiometer. As you can see, there's this battery E1, which is definitely the battery of the potentiometer. Its EMF is known. E is the battery whose EMF is not known. E is also the battery whose internal resistance is not known. So basically, in this second loop, we have connected a battery with an EMF E and an internal resistance small r, and we have to determine the EMF E also and the internal resistance small r also. If there was no internal resistance, it would have been easy to determine the value of E, isn't it? We would just have connected a known battery and obtained a length for zero current L1. We would have connected an unknown battery, the battery E, and then we would have obtained a length L2 for zero current in the second loop. Then we would have said that E unknown by E known is L1 by L2. But in this case, this battery does have an internal resistance. So in this case, the procedure will be different. First of all, we calculate the value of C for which the current in the second loop is 0. Now when we do that, the length, CB, for which I2 is 0, the current in the second loop is 0, comes out to be L1. So the value of E is now I into rho into L1, isn't it? After all, plus E minus I into RCB equal to 0. This is because there's no current passing through the small internal resistance R in case of zero current. You see I2 equal to 0. So you don't have to include the internal resistance when you apply Kirchhoff's law here. Therefore you can say that E is equal to I into rho into L1, where rho is the resistance per unit length of this resistance wire AB. Now we do something different. We connect an external resistance R in parallel here, like this. So as you can see, we have connected an external resistance capital R in parallel with the battery whose EMF is unknown and whose internal resistance is unknown. Now we again find out the point L2, for which the current through the second loop is 0. As you can see, this length is L2 now. The distance between C and B is L2, for which the current I2 through the second loop is 0. In this case, we can now say that V is I into rho into L2, isn't it? You see, the thing is that in the earlier case we had applied Kirchhoff's law in the second loop and said that plus E minus I into RCB equal to 0, and then we had said that E is equal to I into rho into L1. That's what we had said. In this case, however, there is some current passing through the internal resistance, isn't it? You see, in this case, E minus I into RCB minus I dash into R is equal to 0. That is because there is a current I dash in this loop, isn't there? This current has not become 0, and since there is a current I dash in this loop, therefore we can replace E minus I dash R by V, and we can say that V minus I into RCB is 0 in this case. So basically, in the earlier case, E was I rho L1. In this case, V is I into RCB equal to I into rho into L2. So therefore we have two equations. E is I rho L1 and V is I rho L2. Using these equations, we get the value of E by V as L1 by L2. Now remember, we had calculated the formula for internal resistance in terms of the external resistance capital R, and the EMF of the battery E. We can use the formula E by V equal to L1 by L2 in that expression to get the value of the internal resistance. You see, small r was capital R into E by V minus 1, but E by V is L1 by L2, and therefore the internal resistance of the unknown battery can be calculated like this. The core concept that we used here was that first we connected the unknown battery just as we had done in the previous case, here in this circuit, and then we calculated the current equal to 0 point. We then said that E is I into rho into L1. Then what we did was that we connected an external resistance capital R in parallel with the battery. When we did that, we again calculated the current equal to 0 point, and then we said that in this case V, the net potential difference across the battery, is equal to I into rho into L2. That is because in this case the current through the third loop, the new loop, was not 0, and so the internal resistance did have a contribution to the potential drop across the battery, and therefore we could not write E minus I into rho into L2 is 0. We had to write V minus I into rho into L2 is 0. When we did that, we obtained the ratio E by V as L1 by L2. Now we use the formula small r is capital R into L1 by L2 minus 1, because that formula was small r is capital R into E by V minus 1, and we replaced E by V by L1 by L2. Now again, this might seem a bit complicated, but if you replay this whole concept of a potentiometer again and pause, think, and again play it, you will definitely understand. This was the concept related to a potentiometer. Let's now move on to the next concept. The next concept that we are going to study is the principle of Wheatstone bridge. Now imagine resistances connected as shown on your screen. As you can see, there is a battery of EMF E. Connected to the battery of EMF E are 4 resistances P, Q, R and S, and they are connected as shown in the figure. As you can see, this point between P and Q and this point between R and S are joined. These 2 points are joined together. So a current I is flowing from the battery and it is splitting up into 2 parts, I1 and I2 here. Understood? Now, what if the galvanometer shows 0 deflection? You see, it has been found that for certain values of resistances P, Q, R and S, the galvanometer shows absolutely no deflection. What that means is that absolutely no current passes through this central wire, the wire in the middle here. So all the current, it just splits up into I1 and I2 and then it gets rejoined here, I1 and I2, and flows back to the negative terminal of the battery. There is no splitting up of the current here at this junction and at this junction. Now suppose, that the galvanometer is actually showing 0 deflection. In that case, we can apply Kirchhoff's law in this loop like this, in the loop containing P and R. As you can see, minus I1 into P plus I2 into R is equal to 0, isn't it? That is simple Kirchhoff's law. Similarly, we can apply Kirchhoff's voltage law in the second loop. When we do that, we can again write minus I1 into Q plus I2 into S is 0. Again, I've used the values of the same currents, I1 and I2, because I1 continues undeviated like this. After all, the galvanometer deflection is 0. Similarly, I2 continues undeviated like this across the resistance R, because again, the galvanometer deflection is 0. Therefore, on simplification of these 2 equations, we get the condition P by Q is R by S. So this means that if the resistances are arranged in such a ratio that P by Q is R by S, then the galvanometer deflection through the middle wire will be 0. This condition is called the condition of a balanced Wheatstone bridge. The arrangement of resistances as shown in the figure, with the middle wire, coming from the middle of P and Q and joining the middle of R and S point, is called a Wheatstone bridge. And the Wheatstone bridge is balanced when the galvanometer deflection is 0. Interesting, isn't it? The principle of Wheatstone bridge is sometimes used to calculate the value of an unknown resistance. So let's say you have an unknown resistance P. This P here is unknown, and let's say R and S are known. Now we take Q as a variable resistance. R is a fixed resistance that is known, S is a fixed resistance that is known, and Q is taken to be a resistance that can be varied. When we do that, we keep on varying the value of Q until 0 deflection is obtained in the galvanometer. At the instant when 0 deflection is obtained in the galvanometer, we know that the ratio P by Q is now equal to R by S, isn't it? So Q is varied until P by Q is R by S, and therefore the value P can be obtained as R by S into Q. So to calculate the value of an unknown resistance, we make connections as in the case of a Wheatstone bridge, and we make 2 resistances R and S fixed, and we keep on varying Q until a stage is reached when the galvanometer deflection is 0. When that is so, P by Q is R by S, and the value of P can be obtained. Simple, isn't it? This concept is very fascinating, and many questions are often asked in IIT JEE related to this concept. Let's have a look at some of those questions. Let's look at this one first. This question was asked in IIT JEE 2002. Find the effective resistance between points P and Q of the electric circuit shown in the figure. So basically there are 2 points P and Q, and we have to calculate the equivalent resistance between these 2 points. Now at first glance, that seems to be very difficult. After all, these resistances are neither in series nor in parallel. There's this resistance here in the middle, this resistance here in the middle. So how do we calculate the equivalent resistance? We will calculate the equivalent resistance in this case using the principle of the Wheatstone bridge. If you observe carefully, the resistances here This resistance 2R, 2R, R and R form a Wheatstone bridge, isn't it? It's a balanced Wheatstone bridge. That is because, as you can clearly see, 2R divided by 2R is equal to R divided by R equal to 1. Just as remember P by Q was equal to R by S, similar to that, this and this, they form a Wheatstone bridge. Similarly, these four resistances also form a Wheatstone bridge. R, R, capital 2R and 2R here. All of them form a Wheatstone bridge because again R by R is 1 and 2R by 2R is 1. Now since there are two Wheatstone bridges here, we can remove this 2R resistance in the middle and we can remove this 2R resistance in the middle. That's because no current passes through this middle line at all, isn't it? So we can remove these resistances because there's no current. Now the circuit has become so much simpler. As you can see, now these two resistances are in series, these two are in series and these two are in series. When we combine them, we get this, and we get three resistances in parallel, 4R, 2R and 4R. On simplification and using the formula 1 by R equivalent is 1 by R1 plus 1 by R2 plus 1 by R3, we get the final value of the equivalent resistance of this circuit as 2RR divided by R plus R. So basically all we did was that we detected two Wheatstone bridges and then we disconnected the middle resistances because no current was flowing through those resistances, and then we got a simple series parallel combination that we could easily solve. So wasn't this IIT JEE problem really simple? Of course it was. Let's now move on to the next one. This problem was asked in IIT JEE 1996. Calculate the potential difference across the resistor of 400 ohms as will be measured by the voltmeter V of resistance 400 ohms. So we are given this circuit that you see on your screen. In this circuit, as you can see, there is a resistance of 400 ohms here. A voltmeter is connected in parallel with this resistor of 400 ohms. We have to calculate the voltage reading of the voltmeter. So how will we proceed? As you can see, we can replace the voltmeter by a resistance of 400 ohm because the resistance of the voltmeter is 400 ohms. We basically have to calculate the net potential difference across these two resistors of value 400 ohms. You don't have to worry about words like calculate the potential difference as detected by the voltmeter. So what will the voltmeter detect? What will be the actual potential difference? Don't be worried. You can just replace the voltmeter with a resistance of 400 ohm and then proceed to calculate the potential difference across these two resistances of 400 ohms value. Now let's simplify this resistance circuit. As you can see, these two 400 ohm resistances are in parallel. So they can basically be replaced by a single 200 ohm resistance, isn't it? When we replace those two 400 ohm resistances with a single 200 ohm resistances, we detect something weird. We detect that a Wheatstone bridge has been formed. A Wheatstone bridge. If you look carefully, you will see this is the 100 ohm resistance, this is a 200 ohm resistance, this is a 200 ohm resistance, and this is a 100 ohm resistance. If you join these two resistances like this, don't you see a Wheatstone bridge forming with this 100 ohm resistance as the middle resistance? Observe carefully. Can you detect the Wheatstone bridge? And as we had said, this is P, this is Q, this is R and this is S. And we had said that P by Q should be R by S, and in this case P by Q is 1 by 2 and R by S is also 1 by 2. And that tells us that this is a balanced Wheatstone bridge. Therefore, this 100 ohm resistance can be removed because there will be no current passing through this middle wire, isn't it? How fascinating. When we remove this 100 ohm resistance, this is what we get. So now we can see the clear picture of the Wheatstone bridge. We can see that a current 1 by 30 amperes flows through each branch of this Wheatstone bridge. This is because the net resistance in the second branch is 300 ohms and the net resistance in branch A is also 300 ohms. So the net current through branch B will be V by R, that is 10 divided by 300 equal to 1 by 30 amperes, and the net current through branch A will also be 10 divided by 300 is equal to 1 by 30 amperes. So that is the reason a current 1 by 30 amperes flows through both these branches. That also means that a current 1 by 30 amperes flows through this 200 ohm resistance. Now the fact is that this 200 ohm resistance is actually the combination of the two 400 ohm resistances that we were given. One 400 ohm resistance that was given in the circuit and the voltmeter which has a 400 ohm resistance, isn't it? So this 200 ohm resistance is the same as this circuit here, consisting of the 400 ohm resistance and the voltmeter. Remember we had calculated the equivalent resistance of these two resistances and replaced this circuit with 200 ohms. What that means is that the potential difference across this 200 ohm resistance is the same as the potential difference across the voltmeter and the potential difference across the 400 ohm resistance, isn't it? Because those two resistances were in parallel, and therefore the potential difference across the voltmeter is simply 1 by 30 into 200, that is 20 by 3 volts, and therefore the final voltmeter reading is 20 by 3 volts. Did you see how using some smart work we actually solved this complicated IIT JEE problem in minutes? I think that's what's important in IIT JEE, using smart work to solve the problems rather than hard work. So there you go. We've solved this IIT JEE problem. Let's now move on to the next concept, the concept of a meter bridge. A meter bridge is a device used to calculate the value of an unknown resistance using the Wheatstone bridge principle. You see, a meter bridge consists of two resistances, P and Q. One of these two resistances is unknown. Now there's this resistance wire, this yellow wire that you see on your screen. This is the resistance wire, and it's placed right below the two resistances P and Q. A jockey, this brown jockey with a galvanometer, is moved across the resistance wire like this. Now when it is moved across the resistance wire, there comes a point when the galvanometer reading is 0. Now when the galvanometer reading is 0, in that case, if the length to the left is L1 and the length to the right is L2, P by Q is L1 by L2, isn't it? You see, according to the Wheatstone bridge principle, when the galvanometer reading is 0, P by Q was equal to R by S. In this case, instead of resistances R and S, there are two branches of this resistance wire. This is R and this is S. As the jockey is moved, the values of R and S both change. However, when the galvanometer reading is 0, P by Q exactly becomes equal to R by S. Now R can be written as rho L1, that is the resistance per unit length into length. Similarly, S can be written as rho L2. So P by Q is L1 by L2 at the point when the galvanometer reading is 0. Now if we know Q, L1 and L2, we can easily find the value of P, isn't it? And that is how a meter bridge works. One important fact that you must remember in case of a meter bridge is that the length of the resistant wire is generally taken to be 1 meter. So even if that length is not given to be 1 meter, you will have to assume it as 1 meter. After all, that is why a meter bridge is called a meter bridge and not a Wheatstone bridge. So shall we solve an IIT JEE problem related to the meter bridge? Let's solve it. This problem was asked in IIT JEE 2002. A thin uniform wire AB of length 1 meter, an unknown resistance X and a resistance 12 ohm are connected by thick conducting strips as shown in the figure. A battery and galvanometer with a sliding jockey are also available. Connections are to be made to measure the unknown resistance X using the principle of Wheatstone bridge. Are there positive and negative terminals on the galvanometer? Show the battery and galvanometer with jockey connected at appropriate points. After appropriate connections are made, it is found that no deflection takes place in the galvanometer when the sliding jockey touches the wire at a distance 60 centimeters from A. Obtain the value of x. Now this problem appears really complicated at first glance. This system that they have shown, the diagram, it appears somewhat similar to a meter bridge, isn't it? But it is still different from a meter bridge, because in the case of the meter bridge that we just saw, the resistance wire was connected from B to D, isn't it? But in this case, the resistance wire is connected between A and B. So what is happening? Let's solve this question part by part. First, let's look at the first part. Are there positive and negative terminals on the galvanometer? Well, our purpose in case of a galvanometer is just to detect current. So if there is current, the galvanometer shows deflection. If there is no current, the galvanometer does not show deflection. When we have to measure current, we use an ammeter. When we have to measure voltage, we use a voltmeter. So in the case of a galvanometer, there are no positive and negative terminals. That is because we don't need the direction of the current. All we need is to detect whether the current is there or not. An ammeter and voltmeter, however, have positive and negative terminals because they determine the direction of the current and the direction of the voltage. Now let's move on to the second part of the question. Show the battery and galvanometer with jockey connected at appropriate points. Well, in case of a meter bridge, we had learned that if this was the resistance P and if this was the resistance Q, then the resistance wire was connected like this. And you know the length of the resistance wire was 1 meter. And then we had used a jockey like this. And we moved the jockey, across this resistance wire. Here to there, there to here, until zero deflection in the galvanometer here was obtained. Correct? In this case, the resistance wire has been connected here. So basically what you can say is that instead of being connected from B to D, the resistance wire has been connected from B to A. But the principle is the same. In this case, point A and point D can be assumed to be at the same potential. So basically you can actually replace this circuit with something like this. What you can say here is that the galvanometer can be connected like this. And this can be the jockey. And the jockey can be moved from here to here, here to here until a zero reading is obtained. Terminal A is simply the equivalent of terminal D. Now when you move your jockey across this resistance wire, there comes a stage when a balanced Wheatstone bridge is created. That's because this resistance is the same as P, this is Q, this is R, and this is X. So when P by Q is R by S, a balanced Wheatstone bridge is created, and when that happens, we can calculate the value of the unknown resistance P, that is X. Now it might be very difficult to visualize how this situation is the same as that of a Wheatstone bridge or a meter bridge, but it is the same. Observe carefully and you'll understand. So where do you think we will have to put the galvanometer and jockey? We'll put the galvanometer and jockey right here. Now where do we put the battery? Clearly, the battery must be connected between B and D. That's because in this case, as I said earlier, terminal A has simply replaced terminal D. So in the case of a meter bridge, remember the battery was connected between B and D like this? And the resistance wire was somewhere here like this. In this case too, the battery can be connected between B and D like this. The battery can also be connected between B and A because A and D are one and the same. So these are the connections of the galvanometer, the jockey and the battery. Now we come to the third part of the question. After appropriate connections are made, it is found that no deflection takes place in the galvanometer when the sliding jockey touches the wire at a distance of 60 centimeters from A. Obtain the value of X. Now this is again very simple. It is given that the deflection in the galvanometer is 0 when the distance of this point where the jockey touches the resistance wire from A is 60 centimeters. We have to find the value of X. Now, using the condition of Wheatstone bridge, we can clearly say that X divided by 12 is the same as this length, say L1, divided by this length, L2, isn't it? That is because, see, this is P, this is Q, this is R, and this is S. In the case of balanced Wheatstone bridge, P by Q is R by S, isn't it? P by Q is the same as X by 12, and R by S is the same as rho L1 divided by rho L2, that is L1 by L2. Now you can clearly see that X by 12 is L1 by L2, so X by 12 is 40 by 60, isn't it? And when you simplify this expression, this is what you get. The value of X comes out to be 2 by 3 ohms. So that is the final answer for this IIT JEE problem. So as you can see, all this IIT JEE problem involved was a slight modification of the meter bridge to see how the students could apply the principle of the Wheatstone bridge. So that's how most IIT JEE problems are. They have those core concepts and they slightly modify the conventional instruments, to test your core concepts. Let's now move on to the next topic, post office box. The next instrument that we are going to study is the post office box. As you can see, the picture on your screen represents a post office box. Now, what is happening in this picture? As you can see, you can see so many gray squares with black circles in them. You can see P, Q, R. What is this? Actually, the post office box is just a different kind of representation of the Wheatstone bridge. You see, a post office box is also used to find an unknown resistance, and it again uses the principle of the Wheatstone bridge. For a moment, forget about all these gray squares and black circles. Just imagine one single resistance P being connected here, like this. Then imagine a resistance Q being connected here, like this. Now imagine a resistance R being connected here, like this. R is quite a long resistance, so it's coming up till here. So don't you see the signs of a Wheatstone bridge? If you can connect a resistance S here, like this, you can determine the value of S using the principle of the Wheatstone bridge, isn't it? Because P by Q will be R by S. R appears weird and U-shaped, but it's actually only a resistance which is a part of a Wheatstone bridge, isn't it? So P by Q would be R by S. So S would be the unknown resistance in this case. Simple enough. So why are there so many black circles and gray squares? Basically, they are simply to help us choose the proper values of P, Q and R. You see, we can choose P as 1000 ohms, 100 ohms or 10 ohms. Q can assume values of 10 ohms, 100 ohms and 1000 ohms. So at any given instant, P will either have a value 1000 ohms or 100 ohms or 10 ohms, and Q will also have either of these three values. Once you have fixed P and once you have fixed Q, you can now keep on varying R. You see, we connect this external resistance S here between D and C, and then we keep on varying R. At a certain value of R, say this one, the galvanometer current is 0. As you can see, the galvanometer is connected, from between P and Q to a point between R and S. The point between R and S is clearly D if you visualize carefully. So when the galvanometer reading is 0, in that case, P by Q will be R by S. So many variable values of R are given here because we have to keep on varying the value of R such that P by Q becomes equal to R by S, and so that the galvanometer reading becomes 0. So you keep on, varying R. First you consider R equal to 1 ohm, then 2 ohm, then 3 ohm, then 4 ohm, and so on until the galvanometer reading is 0. And then you say P by Q is R by S. So did you understand the principle of the post office box? It's simply the application of the Wheatstone bridge principle. As you can see, this is where S will be connected. So shall we solve an IIT JEE problem related to the post office box? Let's solve it. This problem was asked in IIT JEE 2004. Between which points should the unknown resistance be connected? Well, as you can see, this figure represents a modified version of the post office box. Now clearly, this is where one of the known resistances will be connected. This is where another known resistance will be connected. This here is basically R, isn't it? And therefore, the unknown resistance S must be connected between A and D. Like this, isn't it? One of these circles here represents, which resistance P is. One of these circles here represents what value of resistance Q has. And then we can keep on varying the value of R to get P by Q equal to R by S. The simple answer to where the unknown resistance must be connected, however, is clearly AD. The unknown resistance must be connected between A and D. Understood? So there we go. We've already covered the principle of post office box. Let's now move on to yet another concept. The next concept involves the experimental verification of Ohm's law. In the past few years, IIT JEE has laid extra stress on CBSE lab experiments and on different kinds of instruments. These problems were not asked say 10 years earlier, but in the last 10 years, focusing on these topics which are important for class 12th too has become a trend. So recently, a question related to the experimental verification of Ohm's law was asked. So I'll just briefly tell you exactly how Ohm's law can be verified in the laboratory. Then we will solve the IIT JEE problem that is relevant to this concept that was asked a few years ago. So how do we verify Ohm's law experimentally? Well, we already know what Ohm's law is, right? Ohm's law states that V is I into R. V here represents the potential difference across any element. I represents the current through the element, and R represents the resistance offered by the element to the flow of electric current. Now, how to verify this law? To verify this law, we have this apparatus that you see on your screen. We connect a battery to a resistance R and a rheostat. A rheostat is an instrument used to offer variable resistance in a circuit. This means that a rheostat can offer, high resistance or low resistance depending on the reading of the rheostat. So the main purpose of a rheostat is to vary the resistance in a circuit. So we connect a battery to a resistance capital R, and we connect the resistance capital R to a rheostat RH. We connect the rheostat to a key. Now we record the current in the circuit and the potential difference across the resistance R. We record the current in the circuit by connecting an ammeter like this in series with the battery. We record the potential difference across the resistance R by connecting a voltmeter in parallel with the resistance R. Now if you focus only on the resistance capital R, applying Kirchhoff's voltage law, you can clearly say that if the potential difference across the battery is E, then E minus VR, the potential difference across the resistance R, minus VRH, the potential difference across the rheostat, will be equal to 0, isn't it? This means that VR, the potential difference across the battery, will be E minus VRH, the potential difference across the rheostat. What this means is that as we keep on varying the resistance of the rheostat, the potential difference across the resistance R keeps changing, isn't it? That is obvious because the potential difference across the resistance R is E minus VRH. So when we change the resistance in the rheostat, VRH changes, the potential difference across the rheostat changes, and that changes the net potential difference across the resistance capital R. When we vary the resistance in the rheostat, the current through the circuit also changes, isn't it? Because as we change the resistance, more resistance is offered to the flow of current or less resistance is offered to the flow of current. So basically, by moving the pointer along the rheostat, we keep on varying the value of potential difference across the capital resistance R, and we also keep on varying the current across the resistance R. Now what we do is that we keep on varying the value of resistance of the rheostat, and as we vary this value of resistance of the rheostat, we keep on obtaining the value of the voltage across the resistance capital R and the current passing through the resistance capital R. And then we note down these values for specific values of the rheostat resistance. So we note down something like this. Rheostat resistance value 1 has this value of voltage and this value of current across the resistance R. Rheostat's resistance value 2 has this value of voltage and this value of current across the resistance R. Rheostat's resistance value 3 has this value of voltage and this value of current across the resistance capital R. So basically we note down a lot of voltage readings and current readings as we keep on varying the rheostat resistance. Then, after we've noted down a sufficient number of voltage and current readings across the resistance R, we plot a graph between different values of V and I for different RH values. Now when we plot a graph between V and I, what we see is this. We see that the net potential difference across the resistor R and the net current passing through the resistor R are proportional to each other. The potential difference across the resistor R is proportional to I because the IV graph is a straight line. In fact, if the value of resistance capital R is known, we derive that the slope of the graph, is actually R. And therefore, we verify Ohm's law and we write down V is IR. And that is how the experimental verification of Ohm's law can take place. Let's solve an IIT JEE problem to further understand this experiment better. This problem was asked in IIT JEE 2004. Draw the circuit for experimental verification of Ohm's law using a source of variable DC voltage, a main resistance of 100 ohms, 2 galvanometers and 2 resistances of values 10 raised to 6 ohms and 10 raised to minus 3 ohms respectively. Clearly show the positions of the voltmeter and the ammeter. So basically this IIT JEE problem has given us a lot of instruments and it is basically asking us to draw the circuit to determine the Ohm's law experimentally. When we draw the circuit, this is what we get. You see, the only difference in this case and the case where we just saw and verified Ohm's law is that in this case, instead of a rheostat, we are given a variable DC voltage. So basically the variable DC voltage refers to the rheostat because it is because of the rheostat that the voltage varies in the circuit, isn't it? Again, we're given 2 galvanometers and 2 resistances instead of an ammeter and a voltmeter, but that is simple enough. We can connect the ammeter in the circuit like this by connecting the 10 raised to minus 3 ohm resistance in parallel with one of the galvanometers. So as you can see, I have connected this shunt resistance of magnitude 10 raised to minus 3 ohms with this galvanometer. Similarly, I have connected the very large resistance, the resistance of value 10 raised to 6 ohms in series with this galvanometer to form a voltmeter. So basically we can say that this is an ammeter and this is a voltmeter. And this is the final circuit for experimental verification of Ohm's law. Understood? So that was simple. This brings us to the end of this chapter related to the grouping of cells, the internal resistance of a battery, the Wheatstone bridge principle, different instruments like the ammeter, the voltmeter, the potentiometer. We've studied so many things in this chapter. Let's now move on to the next chapter, which involves the thermal effects of current. Let's proceed.